Hey everyone, this is Mr. Garcia, and in this video, I'm in the classroom. Okay, so I just want to give you a brief view of my classroom, and I'm going to help you understand, maybe, that's my goal, uh, composition, how to use composition of functions to see if two functions are inverses of each other. Okay, so there's a problem here that my students always have questions on, and this is where you can see if your algebra skills are getting better. Okay, so you're given these two functions, and on this assignment, I'm asking students to show or prove if the two given functions are inverses of each other. So if you don't know how to do this yet, okay, this will be your introduction perhaps, and I'm just going to go over this problem. And then maybe if it helps you or my students, it depends if they ask me, I might go back and do another short video and maybe do another problem for them. So I'm going to give you as many details as possible, and I'm going to go slow and explain as well as I can how to use composition to determine if two functions are inverses of each other or not. So let's go ahead and get started. All right, so this is inverse functions with composition, and this is a biconditional statement, which is something we can prove, okay? So this biconditional says that the function f and the function its inverse, which is what this means, are inverse functions if, okay? Notice that in English we use this, but in mathematics this means if and only if, so that's what makes it a biconditional. If and only if the composition of f and f inverse of x is equal to x, and the composition of f inverse and f of x is equal to x. So all this means is very simple, okay? Like I said, the challenge is, can you do the algebra? So I'm going to give you the example that I showed you at the beginning of this video. So the question here is, are f of x and g of x inverse functions? So here is f of x and here is g of x. So what I'm going to do is I'm going to do two columns. On one column, I'm going to show if this is true, meaning that if when I do this composition, I end up with x only on the right-hand side. And then I'm going to do another column and show that if I compose f inverse of x with f of x, I end up with x by itself on the right-hand side again. So this is what I mean. So I'm going to separate this here. Okay, I'm going to do just this line to separate the two. So on this side, I'm going to do f composed of g of x, okay? And on this other side, I'm going to do g composed of f of x. So then I'm going to see, always when you do composition, the first function comes out of this parentheses. So I'm going to have f, and instead of parentheses, I'm going to use a bracket. Because I don't want to get confused on parentheses and brackets, okay? So I usually use a bracket first, and then inside of this bracket, I'm going to have g of x. So this is the first step for me all the time. Now, I'm going to keep f outside, and then inside of the bracket, instead of g of x, now let's look at what g of x is equal to. So g of x is 7x plus 3 over 4. So then I just copy that. Instead of g of x, I'm replacing or substituting for g of x. So 7x plus 3 over, I said 2, it should be 4, okay? So there is g of x. Now let's look at what f is going to do. Okay, so f has a 4 in front of the x, and then subtracts 3 and divide by 7. So whatever you see an x in f of x, instead of that x, replace that x with 7x plus 3 over 4. So I have the 4. And again, I'm going to use bracket here. And then instead of x, I'm going to have g of x, which is 7x plus 3 over 4. And what else does f of x do to this? Subtracts 3, and then it divides by 7. Okay, and then I'm going to close a bracket. But watch what happens here. What's going to happen to this 4 and that 4? They simplify, right? So then all I have left in the numerator, meaning this part of the expression, I have 7x plus 3 coming from here, and this is over 1, which is just this. But then I also have a minus 3 outside of the parentheses. So there's the minus 3, and all of this is over 7, right? So then when I combine the positive 3 and the negative 3, they become 0. So all that's left in the numerator is 7x. And this is 7x over 7. But this simplifies because 7 over 7 is 1. This simplifies to just x. So then the composition of f and g of x is equal to x. So far, check. This one works out, right? Because we get this here. But now we need to do the other side. So then do the same thing. So now g comes out instead of f. So I'm going to have g. And then open bracket. And inside of the bracket, I'm going to have f of x. Now, instead of f of x, I still have g outside. I haven't applied g yet. Okay, I haven't done the composition yet. So then instead of f of x, I'm going to have what f of x is equal to. So this is 4x minus 3 over 7. Now let's apply g to f of x. So then look at g. G has a 7 in front of the x. So then that 7 is here. And in parentheses, instead of f of x, we're going to replace, instead of the x, we're going to replace 7 times 4x minus 3, okay, over 7. So this will be 4x minus 3 over 7. And then g adds 3 outside to this and also divides by 4. All right, so from here, I hope you can see this. Again, we have this 7 and that 7 are going to simplify and it becomes just 1, right? So then I have only what's inside of this parenthesis, that 4x minus 3. But I also have a plus 3 outside. And all of this is over 4. So then we can simplify this even further because negative 3 and positive 3 combine to 0. So all that's left on the numerator is 4x and the denominator is 4. So then this, as you know, simplifies to just x. So then the composition of g of f of x is equal to x. So that means we do satisfy this biconditional. So therefore, our conclusion is that f and g are inverses. Or inverse functions. Okay, so this is the answer to this problem, and I hope that helps you understand function composition. All right, talk to you soon. Bye bye.